So after we discuss the properties of the first essential special function, which is a gamma function, let's switch to the next important special function, which is Digamma function. So Digamma function is the logarithmic derivative of the gamma function. Usually it's denoted as psi of z. So the idea of this model is to explain some basic properties of the Digamma function, to write down its asymptotics, and to study some very instructive example with the usage of this function. So here we go. Most of the properties of the Digamma function follows from the corresponding properties of the gamma function itself. So let's start. First, let's write down very specific value of Digamma function, which is psi of 1, which is simply the derivative of the gamma function taking at point 1, because the gamma function of 1 is 1. So there is no denominator here. And it's denoted as minus gamma, where gamma is so-called Euler constant. It's 0.577. So we'll encounter this constant in the future quite often. Right. So next, let's recall some basic properties of the gamma function, which is, for example, its factorial property. And let's write down the corresponding property of the Digamma function. So we just take the logarithm of both left-hand side and the right-hand side and get psi of z plus 1. So differentiate it, and psi of z plus 1 equals to 1 over z plus psi of z. So here is the mirroring chain rule for the Digamma function. And in fact, we can continue this equation, and actually let's write it down for integer z. So psi of n plus 1 is expressed through the psi of n, and then if we continue, we get the following chain rule. And psi of 1, of course, is minus Euler's constant. So we'll use this equation later on for the proof of some further important properties of the Digamma function. Right. Now the second property. So this was the first one. The second is the asymptotic of the Digamma function. So let's first recall the asymptotic of the gamma function, which is a Stirling formula. Take the logarithm from both parts and differentiate it with respect to z. So when we differentiate it, we get psi of z equals logarithm of z minus 1 over 2 z. Well, as z tends to infinity, of course, and as you remember, the argument of z should belong to the following segment. The modulus of the argument is less than pi minus delta, where delta is arbitrary small number. Right. With this in mind, we can prove the following very useful identity. So the limit of psi of z plus a minus psi of z as z tends to infinity equals 0. And indeed, if you look at this asymptotics, you can clearly see why this is so. So it's just simple ratio of the logarithm of ratio, which tends to 1. So yeah, it's more or less obvious. And now we are ready to discuss some useful representations for their Euler's psi function. So let's first study the following property. So if z is integer, then psi of n from the asymptotics is equal to the logarithm of n minus 1 over 2n, as n tends to infinity. Or rather, since we have this useful representation, we can rewrite this asymptotics for n plus 1. Well, it's slightly more suitable. Again, we just plug in n plus 1 in the logarithm and n plus 1 here, and in the leading order we'll get just the same logarithm, but plus 1 over 2n. Right. Next, we use this chain rule representation for psi of n plus 1. So it's equal to, so the sum from 0 to n, actually from 1 to n, 1 over k, minus gamma, Euler constant. So, and now comparing this approximate expression and this exact expression, we conclude that we can actually subtract these two equations, and the left-hand side will tend to 0, and the right-hand side, well, the left-hand side will tend to 0 when n tends to plus infinity, and the same will happen with the right-hand side. So, and here we go. So it's logarithm of n plus 1 over 2n minus the sum from 1 to n and plus gamma tends to 0 as n tends to infinity. And here comes the most probably beautiful equation which follows from the definition of the Digamma function. So we see that the series, the sum of the series, which has a special name in mathematics, it's called harmonic series, is divergent. And it's divergent like the logarithm of its upper limit, logarithm of n. So the difference between this divergent sum and the logarithm, when n tends to infinity, is equal to gamma, the Euler constant. So this Euler, now its mathematical sense is more or less pronounced, more or less clear, because this constant measures the difference between the harmonic series and the logarithm of its upper limit. Next, let's derive one more suitable representation for the Digamma function, which will be extremely useful when computing, for example, integrals or infinite sums.